Hello everybody, my name is Guillaume Fieni, I'm a PhD student at the University of Lille, and today we present to SelfWatts on-the-fly selection of performance events to optimize software-defined parameters. Data centers try to maximize their power usage effectiveness in order to reduce their operating cost and their carbon footprint, and to improve the management of their resources. This requires the ability to highlight energy hotspot for distributed infrastructure, especially heterogeneous environment like HPC, cloud computing edge, at a fine granularity, so hardware for CPU, memory, GPU, and software, virtual machine and containers, and taking into account various kind of workloads. A lot of work has been made about the energy measurement method, especially about hardware and software parameters, which can provide the power estimations at different levels of granularity, from the power supply of the machine to the hardware like the CPU, GPU, and memory, and down to the software running on the machine. This parameter uses the execution metrics provided by the hardware. For example, for the CPU, it's the hardware performance counters. But this parameter requires some configuration in order to be used, especially requires previous knowledge about the running architecture of the machine. And so this leads to the feature selection of the software power models. So in the literature it's mainly done with the correlation coefficient and the principal component analysis, and they mostly use the learning phases where they run benchmark on the machine. This is offline, of course, so they run the benchmark on the machine in order to capture the behavior of the machine for every performance counter or feature. And at the end, when they finish the exploration, they select the most relevant ones and they will use them in the models. So we will focus on SmartWatts, which is a self-adaptive parameter where no offline calibration phase is required, because it uses the machine activity and inactivity as sample for the learning of its power model. And this parameter provides per container CPU and memory power estimation. It is lightweight and no external hardware is required, and it's also open source. So SmartWatts is based on the running average power limit feature, which provide power camping capabilities, but it can also report the accumulated energy consumption for multiple domains like the package, the core, the integrated graphics, and the memory. It is available on Intel CPU Science Sunday Bridge and AMD CPU Science Zen. It is known to be accurate. There is a lot of work that base the contribution on the power estimation provided by RPL, and some other work that evaluate the accuracy of RPL. So it's used as to provide the reference power measurement for the CPU in SmartWatts. To monitor the hardware-related activities, SmartWatts use hardware performance counters. So they are integrated to the CPU. There is a high amount of available events, but there is a limited amount of slots to monitor the events simultaneously. So you need to select the most relevant events. In our case, it will be the performance event related to the power consumption. And the hardware performance counter are very low overhead. They don't induce performance penalties on the monitored applications. So SmartWatts is based on the software containers, especially the Linux control groups, the C groups. It's used by a lot of software like Docker, Podman, libvirt, systemd in order to separate the different resources used by the containers. And it allows to monitor the performance counter per container using the perf event interface. So, in this paper we propose SelfWatts, which is an extension of SmartWatts. Its goal is to provide per container CPU and memory power estimation, like SmartWatts, but it will have an on-the-fly selection of the performance events, and it will self-optimize its power models over the time. So for the SelfWatts power model, it's the same as the SmartWatts. So its power model are self-adaptive. It uses the machine activity and inactivity as a sample to learn its power model. So there is no offline calibration phase required to learn the power model. The model is frequency specific. So each frequency will have a sample history and a power model, and this is necessary in order to take into account the power consumption optimization of the CPU, especially the voltage and frequency tuning and the idle states. And when the error threshold will be exceeded, it will trigger the learning of a new power model. So in the case of stable workloads, the power model will remain the same until the workload change. And SelfWatts will explore the performance events available on the CPU by randomly picking a set of performance events to monitor. It will use the event set in a new power model, and it will select the relevant events using recursive feature elimination, and it will leverage the feature selection abilities of the linear regression. There is a limited amount of performance counters available on the CPU, so in order to keep exploring the remaining performance events, we need to remove the less important events of the model, if possible. It's not always possible, and we will use the remaining slots with unexplored events in order to complete our exploration of the available events, and in some cases it will increase the power model accuracy over the time. And the goal is to have the best set possible, the most accurate possible for the power model. SelfWatts is based on 3 software components: the controller, which monitors the hardware performance counter on every node, the power meter, which computes the power estimation for every running containers and handles the event exploration, and the database, which will store the samples of the performance counter as the performance estimations. The controller have to be deployed on every node you want to monitor. It will send its samples to the database, where the power meter will pull the sample to compute the power estimation of the running containers, and it will also send the control events to the controller to when it needs to change its events. To evaluate our contribution, we choose to compare SelfWatts to SmartWatts over 3 objectives. the estimation accuracy of the power models, the runtime overhead of the components, and the self-optimization of the power models. The test will be done in 3 environments. This is 3 servers with Intel Xeon CPUs of different generation, one with Skylake, Rodwell, and as well. We will run different workloads from the NAS Parallel benchmark suite, which is an HPC benchmark suite, and StressNG. So for the estimation accuracy, we show that SelfWatts succeeds to compete with SmartWatts, which have the same error on average. We can see that SelfWatts have a lot more of outliers, which is normal because during the exploration you have a lot of bad models, so it increases the outliers due to the error in the estimation, compared to SmartWatts, which won't change its events at all over the experiment. To evaluate the runtime overhead, we use the power estimation of the SelfWatts and SmartWatts components, and we can see on the 2 tables that SmartWatts consume less than SelfWatts, which is expected because SmartWatts have a lot less to handle. It does not do the exploration of the performance events and does not check the relevance of the performance event. So the exploration can lead to a lot of bad power models, which can be costly to learn over the time. So the result was expected. However, we can see that the increase in power consumption is very low. So the benefits that SelfWatts offer are more interesting than the loss in power consumption. To evaluate self-optimization abilities of SelfWatts, we choose to run the same workload on 3 nodes with different CPUs, and we can see on the figure that SelfWatts converge toward accurate model for any architecture. We can see for each architecture that the error stay below the 2 watts on average, and that the error always stay below the 5 watts threshold. And this shows that SelfWatts is able to adapt to different architectures. To conclude, I presented SelfWatts parameter, which use self-adaptive power model to provide per container CPU and memory power estimation. It doesn't use a calibration phase for the performance event and the power model because it explores the performance events at runtime and optimizes its power model on the fly. And it can automatically adapt to the target architecture. And it's open source and freely available on GitHub. Thank you very much for your attention.